Hello. In this video, I will introduce the software QC4Metabolomics. So perhaps I should start with what QC4Metabolomics is, but I won't do that. Instead, I will start with the problem it's trying to solve. And that problem is how to do comprehensive quality control when you do untargeted metabolomics experiments using LC-MS. The problem is the amount of data. Each sample measures thousands of peaks, so how can you know that the data is really a correct representation of your sample? To go into a bit more detail, the main issue is how to check the data comprehensively and across samples. You cannot manually do that because there are too many peaks. Not all problems are apparent to the eye. Minor peaks are covered by major peaks, and even if you did try to do this, you would need a very experienced operator to catch the problems. So what people end up doing is spot checking the data during analysis, or maybe only for a few samples at the beginning. Then all the data is recorded, time goes by, and then the poor PhD student gets around to analyzing the data 2 months later, do a PCA, and see that the data is all over the place. So what to do now? Well, you can try to fix the data by filtering out contaminants or correcting or decreasing the signal, or you can even try to recalibrate the MZ values on the data. But it will never be as good as collecting good data in the first place, and the data might be beyond the point where you can recreate usable data. So either you live with your poor data, or you go back to the lab and spend more time and money reanalyzing your samples. But what if you could have fixed the problem when you analyzed the samples in the first place? For that, you need some tool that in real time figures out that something is wrong, and that is what QC4Metabolomics tries to do for you. So what does it do? The key idea is to take a selection of compounds and monitor them automatically as soon as the instrument is done acquiring a file. We can then plot statistics that show if the instrument is stable. So that is what QC4Metabolomics does. It monitors your LC-MS in real time as the analysis is happening, so that you can deal with the problem right now before it's too late. The setup looks something like this. You can have multiple machines that record data. That is typically done in a proprietary format, so QC4Metabolomics also includes an automatic converter that converts to MZML format. The different modules in QC4Metabolomics can do different automated analyses on the data. That could be checking the accuracy of specific peaks and screening for contaminants. All these results are saved in a database, and then you can easily investigate the data in a web interface. The best way to explain it is to show it, so let me show you what the web interface looks like in action. Alright, let's jump into QC4Metabolomics and see what it can do. When you first open the dashboard, you get an overview of all the files that have been added to QC4Metabolomics. At the top, you can pick your instrument, your project, analyzation mode, and the date range. You can also subset to only files with a certain sample ID. You can see that you have several tabs, and in each of these you find different ways to examine your data. Let's go through it one at a time. I've already put in a date range where I know there is interesting data. Before I start, let me just disclaim that the system was not in use when this data was created. Any issues I show you now are exactly why we implemented this QC system in the lab. Okay, let's get back to the program. On this first tab we have the Track Compounds module. In the first plot, you see the retention time relative to the expected value for the set of compounds I have chosen to track. It's a bit messy when you look at all the compounds at the same time, so let me just limit to tryptophan. You can hover over a sample to see exactly what the sample is. We can see in this first batch of compounds that the samples are around 0.05 minutes from the targets we set, and they are within 0.2 minutes between each other, with the exception of these few samples that behave worse. It might already here be worth investigating why. But anyway, when the positive mode was run and then the next batch in negative mode was run, suddenly the retention times were all over the place. Not good. We will get back to why that happened. But let's scroll down and take a look at the mass values. Again, I subset to just show tryptophan, and we can zoom into the first batch here. In positive mode, it starts out okay, being plus minus 10 ppm apart from the offset. If we again start by the first batch here, we can see that it is systematically offset. So that indicates a calibration issue. In positive mode, it starts out okay, being plus minus 10 ppm apart from the offset. There are two samples here that stand out. If we hover over them, we can see that it's a diluted sample and a blank. So it probably had trouble finding the right peak. But then something went horribly wrong and the ppm goes off, even up to 60 ppm off. So something definitely happened here that would have been nice to know during acquisition. Without this plot, I probably wouldn't notice until later when pre-processing became problematic. Let's take a look at the intensities. Let's look at tryptophan in negative mode. This is where the problem was. Since we have all the samples, it can be a bit difficult to see what's going on. So let's restrict to just the global pools, like this. So now we can see what happened. For the batch with the poor mass precision, we can see that the intensity dropped off to more or less nothing. So probably the signal became so low that the mass accuracy suffered. So it would have been good to stop the instrument here and figure out what the problem is. Of course, back then we didn't have this tracking, unfortunately. For the next project, the problem was evidently solved, even though we see a bit worrying intra-batch drift here. Let's move on from this sad story and check the contaminations tab. We can also go a bit deeper and decrease the threshold for which contaminants we want to include. You can also set if you want to look at the mean intensity or the max intensity. Max is good for contaminants that behave like a peak, while mean or median might be better for contaminants that have a constant presence. So it's like a crime scene investigator for your LCMS. In the heat map, each row is a known contaminant, and the colors show the intensity. And on the x-axis, you have time. For example, you can see here that uricamide suddenly stands out and then goes away. Let's investigate that more by going to the Time View tab. Here we can choose the specific contaminants. And then we can follow it over time. Here we can see that it more or less only appeared in one batch of samples. So it would be nice to investigate what makes these samples unique, or what happened in the lab. Finally, we can also go to the last tab and select a specific sample. Then you will see an overview over all the contaminants that have been found in that sample. We can zoom into the start here and see what the most prominent contaminants are. So here it would be acetonitrile followed by uricamide and a PEG and a lot of other detergent-related ions. Also, DMSO is listed, but in this case it might not be really DMSO, I think, since it is not a solvent we use. Of course, when you screen for 800 contaminants, you might sometimes get false hits, but it gives a general idea about what kind of stuff is in your samples, and in particular if something changed from previous analyses. We also have a productivity tab. That simply shows which projects were run when and how many samples were run each day. Then we can move on to the Warnings tab. Here's where you set your own limits. For example, here it is set to email me if the MZ deviation goes above 40 ppm. But you can set limits based on any of the statistics. So this is your safeguard. To detect MZ accuracy issues, you would not need to check manually. The system will notify you of the problem. There's also a Log tab where you can see what the system is doing, and a Debug tab where you can see technical details about the program. So that was the tour as of August 2024. You can check the GitHub page for new updates. Make sure also to read the paper. You can find the link in the description, and there's also a link to the full documentation. If you want to try the system, then visit the link in the description that shows a video of how to run the demo on your own. Thank you.